I am very happy to start today's talk with Lyne Moser, who's going to be talking on a representation theorem for enriched categories. So please, whenever you're ready.
Okay, thanks. So thanks for the opportunity to talk at this conference. So I was super excited to talk at a conference on double categories because they play a huge role in my studies, in my research so far. And so I'm interested in them mostly to study the theory of two categories, and I think they're a great place to actually do that. And this is kind of like what I'm gonna say today, but maybe also for a more general case, namely that of enriched categories. And so in the first part of my talk, I will tell you what we did with tslil clingman for two categories. And then in the second part of my talk, this is work in progress with Maru Sarazola and Paula Verdugo. And we're trying to prove a representation theorem for enriched categories. So the representation theorem is about understanding universal properties. And as you probably know, universal properties are super useful in mathematics to make many constructions, such as limits, co-limits, adjunction, and extensions. And when you do mathematics, in the end, you use these kind of constructions really almost every day. And these universal properties, they are encoded by the fact that a certain presheaf is representable. So for example, in the case of a limit, you ask that a certain presheaf is representable. I will come back to this in a bit. But this condition in terms of the representability of a presheaf is not always convenient to work with. So for example, if you go to the infinity category work, or you do homotopy type theory, it's kind of hard to have a handle of this category in which your presheaves are taking values in. And so it's hard to model it. And so often what you want to do instead is try to internalize this notion of presheaves and then use this definition instead. And so when I say trying to internalize this representability, what I mean is, for example, as you know, probably, a limit of a functor is the same thing as a terminal object in the category of cones. And for example, in the case of infinity categories or homotopy type theory, this is the definition of limits that is used in order to model limits also in the infinity category cohort. And so I want to start very basic and start with one category theory. And so a presheaf in this case is a functor of a category from a category C, from the opposite of a category C to sets. And we say that it's representable if you can find an object in C together with an isomorphism from the representable functor of these objects to F. So for example, as I was mentioning in the introduction, if I start with a functor, then I can form this presheaf which sends an object C to the set of cones with summit C over G. And then a limit, the functor G has a limit if this functor is representable. So this is like the usual definition of a limit. And similarly, you can also define adjunctions using this representability condition. For example, if I start with a functor from C to D, then for each object D in D, I can define a presheaf which sends my object C to the set of morphism in D from LC to D. And then L will have a right adjoint if and only if all of these FDs are representables. And this is not immediate from the usual definition of an adjunction, but you actually have like one of the naturality conditions that comes for free. And so this is why this results hold. Okay. And so the main ingredient of the representation theorem is a Grothendieck construction. And so a Grothendieck construction takes a presheaf of a C and sends it to a category of a C. And so from a presheaf, I can form this functor where this category is the category of elements of F. So it has those objects pair Cx of an object C in C together with an element X of the set FC. And then its morphisms from Cx to Ty, there are morphisms in C such that this equality is satisfied. So since f is contravariant, n of f is a functor, is a map of sets, from fd to fc. And so I can ask that y is sent to x. And this is the condition that these morphisms satisfy. And so another way to think this Grothendieck construction is as follows. So I can look at it as a category object in sets, whose objects are the coproduct of all these FCs, and then its morphisms are coproducts of the morphisms from C to D in C times FD, because here we see that X is completely determined by the value by F and Y. So this is enough to describe the morphisms of this category. So in the case of limits, so we had this representable functor, and then we can try to compute its Grothendieck construction, and what we find is the category of cones over G. So namely, its objects are pairs of an object in C together with a cone, and then its morphisms are morphisms in C, which make the cone commute. Okay, so now this Grothendieck construction is actually a fully faithful functor. And so when you have a fully faithful functor, you can try to identify the essential image of this functor, and then you will get an equivalence. So what is the essential image? They are given by this discrete fibration. And so we say that a functor is a discrete fibration of a C if it's a functor from a certain category to C that satisfies the following condition. So for all objects in A and all morphisms from a certain object C to the image under P of this A, then there is a unique lift of this morphism where we fix the target. So there is a unique morphism from B to A in A such that it is mapped to G. And another way of seeing these discrete fibrations is by instead looking at the following pullback. And we say that it's a discrete fibration if and only if the target map from the morphisms to the objects of A is the pullback along P of the target map from the morphisms to the objects of C. So for example, the Grothendieck construction is a discrete fibration. And this is what we were hoping for because we want to identify the image of this functor. And if you want to see this, you can simply notice that this is indeed a pullback. Okay, so now let me denote by Phi over C the full subcategory of functors over C, of categories over C spanned by these discrete fibrations. And so then we have that the Grothendieck construction is an equivalence of category between the category of presheaves over C and the category of discrete fibrations over C. And so the representation theorem is kind of a corollary of this fact, but you need to work a little bit. And then you can show that a functor f from C up to C to set is representable if and only if its Grothendieck construction has a terminal object. So for example, in the case of limit, we would get this characterization that I was talking about at the beginning, namely G has a limit if and only if its category of cones has a terminal object. And just before going to the higher cases, I would like to give another description of terminal objects because this will be useful to generalize to the higher setting. Namely, an object in a category is terminal if and only if the projection from the slice is an isomorphism of category. So these categories has objects, the morphisms to T, and then the morphisms are the commutative triangles over T. And in particular, I can describe this projection as a certain pullback of the source and target map from the category of morphisms in C along this bottom. Okay, so that was for the one categorical case. Any questions? Then I will go to 2. So now we want to look at the 2 category instead. So the definition of a 2 category is simply a category enriched in categories. And so this consists of the following data. So I have a set of objects, and then I have a category of morphisms between any 2 objects. And so this category of morphisms has both objects and morphism, which are given by the 1 morphisms and the 2 morphisms. And of course, I have associative and unital compositions. And so the typical example of a 2 category is the 2 category cat of categories, functors, and natural transformations. And once I have this 2 category, I can define what a 2 presheaf on a 2 category is, and it's going to be simply a 2 functor from C up into cat. So now we have changed, we have gone 1 dimension up, so now we have changed our enrichment, and now set became cat. And so as an example of 2 presheaf, we have again the representables 2 presheaf, and they are given by these 2 functors, which send an object C to the category of morphisms from C to L. Okay. Okay, so now we have 2 presheaf, we have representable functors, so we can say 2 presheaf is representable if there is a representable functor which is isomorphic to it. And here, like, we have this higher data, so this is actually a 2 natural isomorphism. So for example, the way that 2 limits are defined in a 2 category is as follows. So you can start with a 2 functor, and then you can form this similar presheaf to the one that we had before, which sends an object C to the category of cones and modifications between them. So the category of 2 categories now is a free category. So between functors, we do have like the whole structure of a category now. And so then you can define 2 limit of G as an object that represents this 2 presheaf. Okay. And so I want to unpack a bit this definition for you. So if you start with an object, if you have a 2 limit, so a certain object L in C, which represents this functor, then this tells you that you have a 2 natural isomorphism. And so like you have isomorphism of category for any C like this. So between the category of morphisms from C to L and the category of cones with summit C of a G. And this isomorphism of category now has encodes 2 different isomorphisms, like one on objects and one on morphisms. So for example, on objects, you will have that the morphisms from C to L correspond to cones with summit C of a G. And so every such cone can be written uniquely as a morphism from C to L followed by the limit cone. But then you also have the second universal property of the limit, which tells you that the 2 cells corresponds to morphisms between cones. And so all these morphisms between cones can be written as a unique 2 cell followed by the limit cone again. Okay. And so before I go on, I also need the notion of a 2-terminal object. And so a 2-terminal object is simply an object T in a 2 category, such that all the homes to T are isomorphic to the terminal category. Okay. So now we have 2 presheaves. We know what it means for them to be representable, and we would like to try to internalize this notion. So we would like to construct a certain Grothendieck construction. So the first thing you can try is a bit naive, and what you can try to do is start by taking 2 presheaves and then form a 2 category of a C, which has the same objects and morphisms as before. So simply pairs of an object C in C and an object X of the category FC. And the morphisms are morphisms from C to D satisfying this condition. And then we can add two cells because now we want the two category. And so we can say two cells are two cells in C satisfying some condition. But the problem in this construction is that we actually don't see any of the morphisms of the category FC. So in particular, it's not going to be fully faithful or anything. But maybe this is not a problem and the representation theorem doesn't need the whole power of the Grothendieck construction. And you can ask whether the representation theorem does still hold with this definition. So for example, in the case of two limits, do two limits correspond to two terminal objects in this strict two category of cones, which is defined as this Grothendieck construction. And so in this strict two category of cones, we again have as objects the cones with summit C over G, and then the morphisms are the morphisms in C making the cones commute, and this is where the strict comes from because the cones commute on the nose. And then the two morphisms are the two morphisms in C making these cones commute again. But like because of what I said before, that we don't see like any of the modifications or the morphisms between the cones here. This is kind of a problem. And so although it was already known to probably like a lot of two category people, we provided with clingman some very small counterexamples that were showing that a two terminal object in the strict two category of cones is not necessarily two limit. So like one of the two implication is still true, but like the reverse one is not. And this is telling you that this first construction is actually not enough to encode the full data of a two limit. Okay, so maybe what you can try instead is to modify a bit the morphisms in order to also see the missing data of the morphisms of FC. And so this is what I would call the lax Grothendieck construction. And so what we do instead is for the morphisms, we take pairs of morphisms from C to D in C and a morphism from FFY to X. So now it's not just an identity, it's actually a morphism of the category of C. And it seems like we have retrieved the full data of the presheaf now, and this is indeed the case, and Berkeley showed that this lax Grothendieck construction is fully faithful. So now we would like to use this and try to formulate the representation theorem again. And so we could ask, do two limits again coincide with two terminal objects in this lax Grothendieck construction? And so what you can see here is that this lax two category of cones has as objects pairs of a morphism from C to D in C and a modification between the cones. So now it seems like we also see the modifications between the cones. But this is also not true. And actually, with clingman, we have counterexamples showing that both directions fail. So what it's telling you is that the lax slice or this lax two category of cones is not at all related to a two limit via this two terminality condition. But I just want to mention here another approach by Gagnar-Harpa and Lanary, and they actually modify the notion of two terminal objects. And so they consider instead two final objects, and they show that two limits coincide with two final objects in this lax slice. But for this, you need to also consider more data, because like of the Cartesian morphisms. I don't want to get too much into detail because this is not the approach that we're taking here, because we really want to like define, like characterize limits as certain terminal objects. And so the solution is double categories. And so this is a definition of a double category, but since we're day 4, I guess everybody knows what they are now. And so a double category is an internal category to categories. And here is my convention. So at the level 0, I will call this the category of objects and vertical morphism. And at level 1, this will be the category of horizontal morphisms and squares. Okay. And so there is a horizontal embedding of two categories into double categories, which is two categories of horizontal double category. And this is given by sending two category to this diagram here, where like at level 0, I have the set of objects of my two category. And at level 1, I put all the categories of morphisms of my two category. And so this is, this just sees like a two category as a double category for any trivial vertical morphisms. Okay. And this functor has a right adjoint, which is given by the underlying horizontal two category, and it sends the double category to this data. So like its objects are simply the objects of the double category. So the underlying set of objects of A0, and then the homes are these pullbacks. But this is just like taking a double category and forgetting like the vertical morphisms, basically. And so Paré constructed a Grothendieck construction from these two presheaves now to double categories over this horizontal double category associated to C. And this double category of elements has, again, the same objects and morphisms as before. So objects are pairs of an object C in C and a morphism X in FC. And then the morphisms are morphisms from C to D in C, satisfying this equality. And now we have this extra data of the vertical morphism, and this is where we will put the morphisms of the category FC. And so the vertical morphisms, first, they are defined only if the two first variables are exactly the same. So I only have a morphism from CX to SAX primes, and they are precisely the morphisms of the category FC. And then the squares, they are the two cells satisfying some condition. And so again, what we can see is that this just corresponds again to the double category described by this diagram. So where at level 0, we put the co-product of all the categories FC, and at level 1, we put this categories of morphisms from C to D times the category FT. And this is again because X is fully determined by F and Y, and here the phi is fully determined by psi and alpha. So this is enough data. And just as an observation, if we look at the underlying horizontal two category of this double category of elements, we can see that it's precisely this strict two category of elements that I defined before. So like the thing from the first try. Okay. And so now we also need a notion of terminal object, and this was also defined by Paré. And these are the notion of horizontally terminal, if you want, because here we're saying that for every object in A, there is a unique horizontal morphism from A to T. And then for every vertical morphism, there is a unique square from this vertical morphism to the identity at T. And so this is nice because, as if you remember, in the notion of two limits, we had two different kinds of universal properties. So we had an isomorphism on objects. So we had like a first aspect of the universal property, and then an isomorphism on morphism, which was giving us a second aspect. And the fact that these double terminal objects have really two distinct universal properties, promising to formulate the representation theorem in this case. And just a remark again, we can also formulate this via an isomorphism from the slice over T to A. So where this slice is defined again as a certain pullback, where here we put the horizontal. So this is like the horizontal slice. And so here, this is the double category containing a horizontal morphisms. And so double categories are Cartesian closed, and so I have a full double category of double functors from the horizontal morphism to A. And so we say that we can see that an object T is double terminal if and only if this projection is an isomorphism of double categories. And so the theorem says that a 2 presheaf is representable if and only if this double category of elements has a double terminal object. And actually, we did prove this result in a much weaker setting, namely that of bilimits. So bilimits are like also a 2-dimensional kind of limits, but where the universal property is expressed in terms of an equivalence instead of just an isomorphism. And in the case of pseudo-functor, not just strict 2 functors. Okay, so let's go back to our 2-limit example. And so if we apply this theorem, this representation theorem to it, we can see that a 2 functor has a 2-limit if and only if the double category of cones associated to it has a double terminal object. And in this double category of cones, we can see that the vertical morphisms are now encoding these morphisms between the cones that we were missing in the first construction. And so now we have all the data to formulate both aspects of the universal property of a 2-limit. Okay. Any questions so far? Okay, so before going to the enriched case, I just want to mention something related to tabulators, because we have seen them a lot this week, and I also wanted to say like how they play a role in our story. And so what you can see actually is that if a double category A has tabulators, then, so I just want to recall the definition. So a tabulator is like a double limit of vertical morphism. Then you can see that an object T in a this double category is double terminal if and only if it is 2 terminal in the underlying horizontal 2 category. And so you could try to ask like how does it simplify this representation theorem now? So when does this double category of elements have has tabulators? And so it is the case when if you have a certain 2 presheaf and the 2 category you start with has tensors by this arrow category, and F preserves this tensor, then you can show that the double category of elements has all tabulators. And so under the hypothesis of this lemma, then you can show that a functor, a 2 presheaf is representable if and only if its strict 2 category of elements has a 2 terminal object. So now we're back to the first construction, and we're actually saying that in some cases, this is enough to formulate the representation theorem. And so in particular, if we look at the case of 2 limits again, we retrieve a result that was kind of known, because in some cases you can see that the second aspect of the universal property is actually implied by the first one, and namely it's when C has these tensors by the 2. And in this, when C has this tensor by 2, then this functor is so that like it always preserves them. And so you can reformulate this representation theorem for 2 limits as follows. If you start with a 2 functor from I to C, and C has these tensors by 2, then this 2 functor will have a 2 limit if and only if the 2 category of cones has a 2 terminal objects. And so this says that in some cases, it does suffice to have these 2 category of cones. And typically, this is interesting because if you want to compute a limit in categories, then categories have tensors by 2. And so all 2 limits will actually just be 1 limit. And this is what kind of what this theorem is saying. So, yeah. So if you want to compute two limits in cat, then you can simply compute terminal objects in the two category of cones. Okay. So now we pass to the last part of this story, and it's the case of enriched categories. So the enrichment will be a Cartesian closed category with a product and then a terminal object. And I also asked that it has pullbacks because I want to be able to define internal categories into V as well. And I also need that this Cartesian closed category is extensive. And extensive basically means that it has all small coproducts and that they are well behaved in a certain sense. And this is a nice condition because then I can really see that sets are sitting inside of V via this coproduct functor. So I can send a set S to the coproduct of S of this terminal object. And so I can see sets inside of V. And this has also a right adjoint, which is given by the representable functor of the terminal object. And I will call this U because it's like the underlying set or something. Okay, so what's a V-enriched category? So a V-enriched category C consists of a set of objects again, but then the morphisms, they form objects of V. So I have a home object in V for each pair of objects in my category. And again, I have associative and unital compositions, and these are all formulated inside of the category V itself. So an example, so because V is Cartesian closed, then actually it is V-enriched. And it's enriched in the following way. So its object sets is again just the objects of V, but now the homes, they are these internal homes in V, because V is Cartesian closed, I have internal homes. And so I can see it now as a V-enriched category. So now I have a notion of V categories, and I know that V is a V-enriched category. So I can say what a V presheaf is, but first I need to say this. Just before I continue, yeah, I just wanted to say that because I have this inclusion of set into this V, then it induces an inclusion from cat, which are categories enriched of a set, into V categories. And so now I can say the V presheaf. So if I have C a V-enriched category, then a V presheaf on C will still be an enriched functor from C up into V. So V is also enriched, so I can formulate this kind of presheaves. So for example, we again have this representable presheaves, which send an object C to the object in V of morphisms from C to L. And so I have V presheaves, I have representable functors, so I can say when a presheaf is representable, and it's again when it's isomorphic to a representable functor. Okay, so now using this, this is like how like V-enriched limits are defined. So if I start with an enriched functor from I to C, then I can again form this presheaf, and it's indeed taking values in the right kind of enrichment, because the category of V categories is itself a V category. So between any two, no, that's not what I want. It's Cartesian closed, and so between any two functors, I also have an object in V. So I have an object of V cones in V. And so a V-enriched limit is an object that represents this functor. Okay. So now in order to internalize this definition of representability, we're going to need internal categories to V. And so internal categories to V are diagrams like this. So where I have source, identity and target and compositions, and they satisfy the usual relation of a category object in V. So in particular, composition is associative and unital. And so again, as before, I have an embedding of V-enriched categories into internal categories to V, which is given by sending a V-enriched category to this diagram. So before I said that sets is sitting into V, so I can look at this set as an object in V, and then I can take the co-product of all these home objects in C. And Cottrell, Fujii, and Power showed that this internalization functor has a right adjoint, which is given by sending an internal category to this two category, which has a set of object, the underlying set of A0, and then as the morphisms, this pullbacks here. But basically, it's again like extracting some data from the category V, which is kind of forgetting what's in the first row, except for the underlying set. And so now you can again define a Grothendieck construction similarly to before, from V presheaves on C to internal categories to V over this internalization of C. And for this, you can form the same diagram, and you're gonna say that this Grothendieck construction of F is the diagram which has at level 0 the co-product of all these FCs, and then at level 1 the co-product of these home objects of morphisms in C times FT. Okay. And I also want to mention that Beardsley and Wang have another Grothendieck construction, which I would call the lax version of it, because it's more similar to the lax Grothendieck construction for two categories that I was talking about before. And so in particular, it takes value in enriched categories again. So it's not going to internal categories. And so the theorem says that this Grothendieck construction is indeed fully faithful. And so again, we want to understand what the essential image is. And so for this, we can formulate a definition of a discrete fibration using this pullback description that we have seen at the beginning. And namely, we say that an internal functor from A to the internalization of C is a discrete fibration if the target map from A1 to A0 is a pullback of the target map from the morphisms in C to the objects of C. And so an example of this discrete fibration is, of course, the Grothendieck construction again. And so if we denote by fib over C, this full subcategories by and by the discrete fibrations over the internalization of C, then we can see that this Grothendieck constructions that we define actually gives us an equivalence of categories between V presheaves on C and discrete fibrations over C. Okay. Okay, so now we have the Grothendieck construction. We just need a terminal object, and then we will be able to formulate the representation theorem. And so I will say that an object T in an internal category to V is a terminal if this morphism from the slice is an isomorphism in cat V, where the slice is again defined as a pullback of a certain source and target map along this thing. And then what you can show is that V presheaf is representable if and only if its Grothendieck construction has a terminal object in the sense defined above. And so if we apply this to the V-enriched limits, we have that G has a V-enriched limit if and only if the internal category of V cones has a terminal object. So this is like a generalization now of like this result about two limits. And to finish this section, I just want to mention how we could also like generalize this tabulators condition that we had before and like try to have something that is more internal to V categories. And my guess is that if V is generated by some objects in V, so for example, in the case of V was categories, like it was just like this arrow category, and C has tensor by these objects, then, and F preserves them, then I guess that F should be representable if and only if the underlying V category of this Grothendieck construction has a V terminal object. And by V terminal object here, I mean that all the homes to these objects are isomorphic to the terminal object of V. Okay, so to finish, I want to mention some applications. So first, if we take V equals set, then we can see that categories enriched in sets and categories internal to sets are both just categories. And so that's why we didn't see this problem in the one categorical case, because actually these two settings, they coincide. And so in particular, this result would retrieve this one categorical case. And if we take V equals cat, then categories enriched in cat are two categories, and categories internal to cat are double categories. And so this would give another approach to this representation theorem that we proved in the case of two categories. But then you could also say, okay, let's look at n-1 categories instead. And so a category enriched in n-1 category is by definition an n category. And a category internal to n-1 categories, category internal to n-1 categories. But I hope, I think we should find a name for those because they're very useful to study the theory of n categories. And so if we apply this representation theorem to this case, then we can see that the Grothendieck construction now takes values in internal categories to n-1 categories. And so this was not clear, just looking at the case of two categories, because you go from two categories to double categories. So maybe you think, okay, from three categories, I would go to threefold categories, but actually it's enough to go to internal categories to two categories. And so this is also what this result is telling us. And so for example, for the case of n limits, they would correspond to terminal objects in the internal category to n-1 categories of n cones. And this is the approach that we are taking in the infinity setting to construct limits in an infinity n categories with Martina Rovelli and Nima Razek. And actually, I want to mention that the idea for this project actually comes from something that Nima Razek did in the infinity case, because he did construct a Grothendieck construction in the infinity case, which was actually going to some kind of internal categories, but this was not very clear in the infinity case, and now this makes it precise, what's the intuition industry categorical case for this higher Grothendieck construction. And so just one last thing to if the conjecture that I said before is true, then we could also say that n limits in an n category with tensor by this n-1 cell should correspond to just n terminal objects in the n category of cones. And so again, if you want to compute n limits in the n category of n-1 categories, then it's enough to just work inside of n categories themselves. And that's all I wanted to say today. So thank you for your attention.
Okay, thank you ever so much. Let's thank the speaker. And people can unmute themselves or raise hands or type in the chat if they have any questions that they would like to ask. Okay, and maybe while we wait for questions, it's not a question, but I just want to say, like, it's super cool to see this spelt out, like how, like, n-1 categories and categories internal to n-1 categories, even in the case of like v equals cat, seeing how this is spelled out and the fact there's an adjoint to this inclusion, like this is very satisfying and really nice. I enjoyed this part a lot.
Yeah, I think it's really interesting, like to see like how like enriched categories and internal categories like are like closely related actually, and like how internal categories are really useful to study just like enriched categories in general. So
yeah, and it's also interesting, this idea of like internal categories to n-1 categories. Yeah, that's an interesting thing, not n-fold categories, but something different.
Yeah, we should find a name for them. Like, I don't know, something. Yeah,
I think we've used up all the good names. Okay, are there any questions from anyone in the audience?
Hi, can you hear me?
Yes.
Hey, great talk. Thank you so much for the talk. Just a little comment on the names. We encountered internal categories in two-cat, and we call them double two categories. So something like double, something like double n-1 cat category or something like that. Could be
that sounds good.
Great talk. Thank you.
Okay, does anybody else have any questions? Okay, in that case, if we can thank Lyne again for the lovely talk.